Turn this soda bottle over. 5 rounded feet touch the table. Between them, valleys rise toward the center. Engineers call this a petaloid base because its outline resembles petals. But the shape is not decoration. It solves 2 jobs that pull the geometry in different directions. The bottom must resist unwanted movement under internal pressure, and the bottle must make stable contact with a flat surface. Those 5 feet are where the 2 jobs meet. Carbonated liquid is packaged under pressure. That pressure acts on the bottle walls and on the base. The bottom is not exempt just because it sits on a table. If an inadequately controlled center region moves outward far enough, it can approach or pass the intended support level. The bottle can become unstable or rock instead of resting on its designed contact points. That unwanted change is one form of the base rollout problem described in bottle design literature. It is a design risk, not a claim that every plain bottom fails. Curvature helps explain the solution. A curved shell can carry pressure-related loads differently from a plain flexible panel. But a simple, rounded bottom creates another problem. It does not provide a broad, stable resting surface by itself. A designer could add material or choose another base family. This common carbonated bottle solution reshapes one continuous shell. Parts of that shell project downward to become feet. The valleys and central region remain recessed above the table. The result can keep useful curvature while defining a standing plane. Look closely at the anatomy. Each lobe ends in a contact region. The lowest regions together define an imaginary plane across the tabletop. Between neighboring feet, the shell rises into valleys. The center is also kept above that plane in the intended geometry. The feet are not 5 blocks glued beneath an ordinary flat floor. Feet, valleys, center, and body transition are all parts of the same molded surface. Pressure performance does not belong to the feet alone, and the evidence does not say that every foot carries an equal share of the load. So why 5? Start with the honest answer. 5 is common, not compulsory. This selected bottle has 5. A current manufacturer example also describes 5 petal-like feet, while patent literature documents designs with other counts, including 7. The sources do not establish a universal law that 5 is always strongest or most stable. Foot count works together with bottle diameter, valley shape, contact width, material, pressure, temperature, and production constraints. 5 is the visible answer on many familiar bottles, not a magic constant for every bottle. The bottle also has to be manufactured. It begins as a compact PET preform. The preform is heated, stretched along its length, and expanded outward into a mold. The mold contains the detailed foot and valley geometry, but the final result depends on more than the cavity shape. Stretch history and wall thickness distribution change around the bottle. The preform has to stretch into the deep features while retaining a usable wall distribution through the base. That is why a base redesign can change both shape and process settings. More plastic everywhere is not a complete engineering answer. Once molded, the base still has to endure pressure, time, temperature, handling, and contact with production equipment. The valleys deserve attention because they connect neighboring feet through curved transition regions. In one peer-reviewed analysis of a specific petaloid design, the highest maximum principal stress appeared in a valley, and a redesigned base improved resistance in that study's cracking test. That does not make every valley a failure point. It shows why the complete shape matters. Commercial-based designers also discuss stress cracking resistance and resistance to rollout as separate performance goals. Standing is an industrial problem too. Bottles move through conveyors, accumulate against guides, enter packages, and sit in stacked loads. If the feet make poor contact, or the standing surface changes, that can affect movement and stability beyond the kitchen table. A current bottle-based supplier lists foot contact, smooth conveying, pallet stability, material distribution, stress cracking, and rollout resistance as interacting design concerns. That is one supplier's system description, not an independent ranking, but it reveals how many jobs meet at the base. Now compare the soda bottle with a still water bottle. These two specimens use visibly different bases, but the footage alone does not prove why either geometry was chosen. Sources show that pressure-resistant, hot-fill, and ordinary still water packages can face different combinations of pressure, temperature, and processing requirements. That does not mean every water bottle is flat, or that every soda bottle has 5 feet. The exact specimens on screen are examples, not category rules. A third selected specimen adds another visible variation. This PET juice bottle has a rounded square outline, but its base has 5 major, broad, shallow lobes. Each lobe is divided into 2 molded panels. The outline and panel seams can make the count misleading. Count the 5 lobes around the center. Those panels are surface divisions, not 10 separate feet. Return to the first bottle and rebuild the answer. Carbonation loads the base. Curved regions help carry pressure-related loads. The molded shell projects downward at 5 locations on this specimen. Those contact feet define the standing plane, while the valleys and center remain recessed. Material distribution and stretch history affect the finished geometry. The same base must also resist unwanted deformation and remain stable through handling and transport. The 5 feet are not the whole mechanism. They are the most visible part of a complete pressure, manufacturing, durability, and standing system. That is why this bottle does not simply end in one flat panel. Its Petaloid base keeps pressure-resisting geometry above a stable set of contact points. 5 is common, but the exact solution changes with the bottle and its job. Turn another drink container over, and the same pressure problem produces a different hidden shape. A soda can has no plastic feet at all. So why is the bottom of the can pushed inward?